Good afternoon, my name is John Kresse. I'm a controls engineer with Allison Transmission. Here to talk to you about some advantages power shifting automatics have with natural gas powered vehicles. Some of you probably are used to natural gas vehicles, maybe a few of you. How many have driven natural gas vehicles? And you probably have some idea that automatics seem to make sense with natural gas. Maybe you don't understand the full technology behind it, and I hope to show you a little bit about why automatics seem to be good with natural gas. I'm going to talk about spark-ignited engine characteristics first. This presentation is solely focused on single fuel, alternative fuel. So we're not talking dual fuel. They have their own issues. This is going to be single fuel. It applies to compressed natural gas, liquefied natural gas, and propane. By the time the fuel starts making torque, it's all the same to the transmission and same to the vehicle, whether it's CNG, LNG, or propane. We're going to look at some actual test data from manual and automatic transmission upshifts. We're going to talk about how the challenges that spark-ignited engines impose on the vehicle are overcome with power shifting automatics that are equipped with torque converter. And hopefully by the time we get down to simulation, I'll have built up a little bit of credibility, so you might start to believe the simulation that I'm going to show you. But I know, simulations, can't always trust them. You can trust this one. And we'll talk very briefly about optimizing your transmission for natural gas. Actually, I'm going to tell you whose presentation you need to go see that'll handle this one for you. I'm an old Cummins guy. I love diesels. Diesels are they're the king of the commercial vehicle world right now. Basic diesels are hard to beat from a torque response, from a torque efficiency, power density. But the last 15 years with the challenges of the emissions technology, before all the pre-three-letter acronyms, that have kicked in, it's made diesels that much harder to maintain, that much harder to purchase, and it's hurt the reliability a little bit. This is not, I'm not trying to say the engine companies did anything wrong, because obviously they were responding to the emissions legislation. They did a great job at doing what they did, but we are where we are, and so obviously the cost advantages of natural gas fuel is the big reason we're here and we're talking about this. But I think it's wise to remember what's happened to diesels over the past 15 years that have kind of got us to where we are. So spark-ignited engines have issues. They're, from a performance, productivity, and drivability standpoint, there's drawbacks. But hopefully we'll see that if you use a power shifting torque converter equipped automatic, these limitations can be turned into non-issues and can be overcome without sacrificing fuel economy. So here's some of the characteristics of the spark-ignited natural gas engines. First of all, they have lower clutch engagement torque. So from an automatic perspective, that doesn't matter. We don't launch at the idle governor. But a manual transmission or an automated transmission, they do. They launch at the idle governor. The clutch engagement torque is often less with a spark-ignited engine, as is the torque response at the idle governor is not quite as good. It doesn't pick up the load as well. Torque response is obviously slower. And why is it slower? Well, the fuel is being injected in the intake manifold. And there's a throttle plate involved, and there's also an exhaust oxygen sensor. And that control loop is it makes the torque response a lot slower. Diesels, you squirt in fuel, you get torque. Natural gas, you have to take it into the intake manifold. As this gentleman from Cummins Westport says, and it results in the slower torque response. The torque density can often be lower for natural gas engine. The same size displacement engine doesn't have as much torque. Sometimes to get that torque, or the power from a smaller engine, they have to run it at higher speeds, and that could have its own issues. All natural gas engines, with the exception, all single-fuel natural gas engines, with the exception of the ISX-12G, do not have exhaust or compression braking. So that can be an issue. And with any throttled engine, any engine with a throttle plate, as you get lighter in load, your fuel economy worsens. The BSFC gets a lot worse. Versus an unthrottled diesel, where, yeah, at light loads, the fuel economy, the efficiency can get worse, but with a throttled engine, it really can fall off. So in a few slides, we'll talk about how an automatic overcomes these. But first, let's talk a little bit about operational efficiency. The natural gas commercial trucks, they're still work trucks. They still need to get the job done. And how do we get the job done? We get horsepower to the wheels. And you want to do this in all phases of the drive cycle. The launch, acceleration, deceleration, cruise. You put a number of these together, there's your drive cycle, and that's your day. So, you know, it sounds simplistic to break it down into just a few different small phases, but you can build those up, and you can turn this into a real drive cycle if you want. The low power to weight ratio for a commercial vehicle, it causes issues. The torque response causes a much worse issue with the low power to weight vehicles versus if you had this in a passenger car. It's not as big a deal to have a slow torque response in a passenger car, but with a commercial vehicle where you need to get the job done, it can make a difference. So hopefully we'll look at some things here where power shifting automatics with torque converters will overcome these problems. So this is a upshift with a manual transmission. The blue is engine speed. The red is output speed, so output speed of the transmission. This magenta color is engine torque. This light blue is the accelerator pedal, and boost pressure is the green. So what ends up happening here during your manual transmission or automated manual transmission shift, time to make that upshift, what do? You have to go to zero accelerator pedal. An automated manual still does the same thing, it just does it sending a torque limit or a torque command. So it takes some time. So during that 1.2 seconds approximately where there's no engine torque, there's also no output torque. And if you look at output speed, this is a pretty, relatively quick shift. This is 1.2 seconds. Output speed is actually decreasing. So during a wide open throttle acceleration, the output speed actually slows down. And you can see this is reflected in boost pressure too. The zero torque, boost pressure is dropping. So the loss of torque causes output speed to decrease. And the fact that this is a slow torque response, a diesel upshift may have with a manual may have something similar, but the fact this is a slower torque response makes it all the worse. It exacerbates this zero output torque problem. And then it takes time for the torque to build back up. And right here you see, this happened to be a synchronized manual transmission. So right here the driver was, I guess it wasn't coming down quite fast enough, and the driver was, he was ready to do his shift. So there's slip across the synchro, and that can help, that can degrade the durability. And an unsynchronized transmission, that just means it can take longer to do the shift. Now a power shifting transmission, There's no loss output torque. We see engine torque decrease very, very slightly, but this is just going up the torque curve at the higher speeds. Boost pressure is stable, and the shift is not impacted by the slow engine torque response. You don't have to build the power back up because you never reduce power to begin with. So we're going to move on to attributes of a torque converter. We talked about the shifts there, and torque converters are the kind of the other attribute that helps the power shifting automatics work well with spark ignited engines. Torque converters are great launch devices. They allow fast axles. So fast axles mean low numerical axles. So they allow good startability with the fast axle. And the fast axle also provides low cruise engine speed, which is beneficial too. So that's the reason why you want to use a fast axle, but launching can be difficult. Torque converter helps you do that. Torque converter takes the engine torque and it multiplies it. It provides torque multiplication. You're not just launching with the engine, you're launching with the engine, and we'll look at it on the next slide, with some amount of multiplication. It's more efficient than a slipping clutch during launch. There's also no wear components in a torque converter, and it's productive in stop and go, good in the mud and the snow. And another good thing about it, and it kind of goes into the startability, but a torque converter almost acts as a variable first gear. It provides, you can have a 6-speed with a torque converter, and it's really about an 8-speed transmission. It gives you a couple extra effective ranges. Now this just talks about the good things about torque converters. They're not perfect. There's a couple bad things about them. You don't want to run around all day with the torque converter. And so what you want to do is you want to lock up the torque converter, which takes the fluid path out of the torque path. At Allison, we typically lock up in second range and sometimes in first range. So you use torque converters to launch, then you lock up, and you don't get impact. The fuel economy is not impacted by the use of the torque converter. Here's a chart that is compliments of our friends at Cummins. Basically has the ISL torque curves. And here's clutch engagement torque, and it's listed as 500 and some foot-pounds, 550 down here. A transmission with a input clutch is launching typically at this torque right here, at idle torque. Now you can have a driver that wants to launch at a higher speed. They step on the engine and then they drop the clutch. That's not good for durability. So typically the drivers are taught to launch at idle governor. But this is quite low, 550 foot-pounds. And remember, the torque response is kind of low. It's not picking up the load real well. Now with a torque converter, it actually launches somewhere in this area. It kind of depends on your characteristics. Are you on a grade? How hard you are into the throttle? But the torque converter starts to launch the vehicle somewhere in this area. So it's not impacted by the low idle governor. Plus, not only are you operating at a higher engine torque, but you get torque multiplication. Typically, and I think other manufacturers are similar, but our torque converters are between 1.7 and 2.5, 2.6 torque ratio at a stall condition. So you're getting higher torque, higher engine torque here, plus it gets multiplied by the torque converter. You have just that much more torque to launch. So to summarize the characteristics, remember we had lower clutch engagement torque. Well, the torque converter equipped automatics launching at a higher speed and getting the torque multiplication from the converter. The slower torque response, the wet clutches, they will do the work to make sure the shift gets done quickly. And also during low torque downshifts, it'll pull it up. it'll pull up the engine speed. Lower torque density. And this is true even with diesels. You can have a lower powered and lower torque engine, and because you're not interrupting torque all the time, you can accelerate quicker. So a power shifting automatic on level ground can promote the concept of engine downsizing. You can pick a smaller engine to do the job. Reduced exhaust or compression braking. The 3000, 4000 transmissions have an integral output retarder, so it can also do engine braking. Actually, output braking can provide negative torque when you need it, going down hills or other situations. And the poor BSFC at light loads. We talked a little bit here about engine downsizing. Well, if you're able to run a smaller engine, run that engine at higher load, you're using less throttle plate, that's more efficient. But you want a transmission that can enable that for the level ground. So a power shifting automatic can lead to increased operation at the more efficient operating points. So here's a simulation. This is a small Class 8 at 52,000 pounds. Before we get too far, let me explain what this is. The vehicle speed's on the left. Engine power is here. Engine speed is here. The red is any kind of torque interrupt transmission. The green is an automatic. The duty cycle this is trying to do is simply an acceleration of 45 miles an hour. It's not a wide open throttle acceleration, but it's a pretty moderate to hard acceleration. So both vehicles are just trying to do the same thing. And so let's run it a little bit, and then we'll talk about all right. Well, we see here's the automatic in green. Because it's able to power shift, it can keep it accelerates okay. Every time a torque interrupt is done, remember back a couple slides ago, we saw real data, torque interrupt upshift was done, output speed actually decelerated. So you can see the deceleration. On engine power, the automatic is able to maintain engine power because it's able to do a full power shifting. The manual, every time it wants to do a shift, it's dropping to zero engine torque, which is also zero engine power. And then for engines, well, here, let me run this just a little more. So here's the reduced vehicle acceleration. And when it is in gear, the manual needs to run at a higher power in order to try to make up. It doesn't quite make up, but eventually it does get to 45 miles an hour. But it has to run at these higher powers because it runs at zero power for a little bit, and then the slow torque response prevents the torque or the power from getting to the wheels. So every time it runs, it does a shift, it's going to have to try to catch up. Well, to run higher power, you have to run higher speed. And to run higher speed, that's inefficient for an engine. You'd prefer the engine to run at a constant power and low speed, and like a CVT might be able to run. But of course, commercial CVTs aren't really available, and they could have their own issues. But a power shifting automatic kind of emulates that, keeps the power up and prevents operation at the high or the less efficient engine speeds. So what happened here? This is from a stop to 45 miles an hour at the 1 mile mark. So both vehicles went 1 mile and at 45 and got to 45 miles an hour. The automatic did it faster, 6% faster, and used 1.6% less fuel. And the fuel units I'm using here are diesel gallon equivalent. Most of you are probably familiar with that term, but it's the equivalent energy content that a gallon of diesel would have. It is one method for purchasing fuel when you buy natural gas. The bottom line on this is slower is not always better for stop and go duty cycles. So faster, use less fuel. So how do you optimize your power shifting transmission? Well, you go see my colleague's talk here on Thursday, and he's given a talk on how do you optimize a diesel. And for natural gas, it's the same. It's the same selection of axle ratios. It's the same selection of shift schedules. It's the same process that was used to optimize a diesel. The one caveat is you may select a lower capacity torque converter. And all this does is this allows the engine to rev up quicker because the torque converter is preventing or providing less load to the engine at launch. So this is one of the last slides, but I think it kind of summarizes with one problem here that we'll get to. It's a quote from truckinginfo.com. The engine brake did an admirable job keeping the speed in check coming down the hill and even initiated a downshift. So remember, the ISX-12G is the only spark-ignited engine with an engine brake. But in this case, the automatic gave a downshift that helped the greater output torque to be provided on the vehicle, which helped the retarding effect during while it was going downhill. And then the driver talks about how speeds were kept low, engine speeds were kept low. So the transmission was able to keep the engine in an efficient range. Now from a transmission control engineer perspective, there's one thing on here that offends me a little bit in that the driver or the writer of this talks about the engine initiating the downshift and the engine initiating the upshift, when in reality it's the transmission controller. The engine is just providing the torque. It's the transmission that's managing that torque and that speed. So anyways, there's a lot of reasons why most CNG, spark-ignited CNG and LNG applications in North America and Europe are equipped with power shifting automatics, and most of them made by Allison. And again, it's the ability to do full power shifting and also with the torque converter launch. So that's all I had. You guys, are there any questions?
Your example
Yeah.
was with the Class 8. I assume is it the same for the mid-range?
The simulation example, yeah. That was actually a 3000 series, so it was like a baby Class 8, 52,000 pound. But yeah, it's the same. Some of the smaller natural gas engines have a slightly faster torque response, but it's still the same. Yeah. Yeah.
With a synchro mesh automated manual, when you're using the engine to retard motion of the vehicle, does that automatically downshift also? And if so,
Yeah, that's a good point, and I think I meant to say that on that. When you're coming downhill with an automated manual and it's time for it to do a downshift to help your engine braking, well, for that 1.2 to 1.5 seconds that it's zero output torque, it's also zero negative output torque. So, and that is an area where the power shift transmission does shine. But
So you're able to, with the automatic, maintain constant negative.
exactly, that's right. That's right. Yeah. Is there anything else? All right, thanks.